Trig, Section 3.2, Applications of Radian Measure. So how can you apply radian measures, just a real number? Well, let's start with our friend, the bullseye. Oops, let's put this back just a second. Our friend, the bullseye, so to speak. Well, I'll get better at that. Anyway, here's the angle theta. It has this radius r, both the sides of this angle is radius r. This length of this is, we'll call it S, arc length. Now, how can we find the length of an arc? This is not arc, this is arc length. Well, if we know that this arc length, if we write a ratio, that entire arc length over the entire circumference is the same ratio as the angle theta over the entire circle, 360 degrees. We could also use radians. So I'm going to use these thetas, but I'm going to write the degree mark here, and I'm going to put, even though you should probably put an R. So that's in radians, and it would be 2 pi radians for that. Well, because the circumference of any circle is 2 pi r, we can put that in for the circumference here. That's over 2 pi r. And we could use degrees, except degrees is nothing that we can probably use to get rid of some of the stuff. But in radians, this does. So I'm going to use the radians. Theta in radians over 2 pi. Okay, now let's rewrite this. If we cross multiply, but not with all 2 pi r, we're just going to cross multiply with the r, leave that 2 pi there. But cross multiply here with everything, both the 2 and the pi. So this is really 2 pi s. And in the denominator, or not, there's just a small denominator of 2 pi. And this is then r theta, theta in radians, and 2 pi. Oops, 2 pi has disappeared because we cross multiplied that. This is just a 1. But what cancels is the 2 pi here. So all we have left is s, that arc length, equals r times the angle in radians. And that's sort of a nice little compact formula for arc length. We can find areas of a bunch of things on the circle now and make it a little nicer. What is the area of a circle? Well, we usually use an A, pi r squared. What is the area of a sector? Well, they use a fancy A for that. I'm just going to use a sort of a capital A for cursive. And it's a fraction of the circle, if you think about it. Let me put my bullseye here again. The sector is all of this area here. And so it's a fraction of the entire area. How do you find that fraction? Well, this angle, theta, and we'll do that in radians, over the entire circle, 2 pi, that's the fraction of the area, pi r squared. So what does this area become? Well, the pi's cancel, and you get 1/2. We use that 2 in the denominator. Theta in radians, and the radius squared. You can put the r squared first. Sometimes it sounds better. 1/2 r squared theta. I think that's how our book writes it. 1/2 r squared theta. Just so theta's in radians. Theta has to be in radians for this stuff to work. What is the area of a segment? Well, let's see. Let's first draw what a segment is, and if I can keep drawing this, maybe eventually I get really good at it. There is an angle, theta. These are the radii. And when you draw in the chord right here, there's an area, the crust of a pie, in a sense. That is the segment. So, how do you find that area? Well, and I'm just going to area seg. And maybe I should use area sec, or say sector even. So this segment, if I take the area of the sector, which is this whole pie, including the crust, and subtract the area of that triangle, the one that uses the 2 radii and the the chord here, then I will have what's left, the area of that segment. So, what is the area of the sector? We already know that. It is, of course you can hear the dog in the background too, 1/2 r squared theta, just so theta is in radians. How do we find the area of this triangle? I'm going to give it to you now and then show you where it comes from, because I'll probably need most of a screen to do it. But it is 1/2 r squared and the sine of theta. If we then pull out, or factor out, the 1/2 r squared, we have left that theta in radians, just a number, minus the sine of that angle. I don't need to put a radian measure here because the sine of that angle in radians, the sine of it in degrees, both the same. I guess I'd probably use that though, just because I already had it here. That's the area of a segment. So remember that one, because we got the area of the segment. Well, are you going to have to memorize that? No. I would memorize the area of a sector, 1/2 r squared theta, just so theta's in radians. And of course you've already measured or memorized this area of a circle. So how do we get this 1/2 r squared sine theta? Well, let's change colors to make this a little more interesting. Let's take a look at that picture again. There's the segment. So this is that triangle. We know a couple of things about this triangle. We know these are the radii, so that's the same thing here. We know this is the angle theta. We don't know the length of the chord, but we usually find the area of a triangle by using this perpendicular height. So, if we go back to our area of a triangle is 1/2 the base, which is r, times the height, which is h. You just have to find out what h is. Let's take a look at this right triangle. What is the sine of theta? From that right triangle is the opposite, h, over the hypotenuse, r. Multiply both sides by r, then r sine theta equals h. So instead of h, I'm going to put in, so 1/2 r and then h is r sine theta. And theta can be in radians or degrees or anything because we're applying that sine function. But notice those r's. So 1/2 r squared sine theta. That's where we get that formula. Like I said, do you have to memorize that? No, not necessary. But we need to do some example problems. And I think we'll save that for, well, no, we can do at least one here. Number 2. Let's move this back again. I'm messing my picture up here. Okay, let's try this again. Number 2. We'll work in this little mess. Number 2, find the length of each arc. And number 2 has a picture. It has the angle of pi over 3. It has a radius of 12, and it wants that arc length. So this is pretty straightforward. Find the arc length. So S equals r theta, just so theta is in radians. Theta is in radians, so it's 12 times pi over 3. Reduce that fraction. This is 4 pi. That's not 4 pi radians. It is, the units are 4 pi, whatever that r was. They don't say in this problem, but if it was inches, then this is inches. Remember that this radian measure is unitless. It doesn't have to be inches. It can be really anything that's necessary. It's just the number of radii. Okay, we'll do another one after this. Okay, still trig. I'm not sure why I'm doing this, why this happens. On up here. Okay, let's try this again. Trig 3.2 examples. We already did. This is, I believe, page. Starts on 103. We did number 2. How about number 6? These are some pretty easy beginning ones. Find the radius. We've got this circle. It has a picture that looks something like this. All the way around from here to here is 7 pi over 4. And I'm assuming then all the way around here, they say is 14 pi. Okay. 14 pi. That's the length. So if S is equal to r theta in radians, this distance S is equal to 7. See, the radius is what we don't know we're supposed to find. The theta in radians is the 7 pi over 4. But if we're supposed to find the radius, how do we find out what S is? Well, if we go back to this, the circumference of the entire circle, 2 pi r, is 2 pi times r, which we don't know. But S is that 2 pi r of the whole circle minus the 14 pi. So this is what S is. Let's put that in for the S here. 2 pi r minus the 14 pi equals r, we'll say 7 pi over 4 times r. We need to solve for r, so we need all the terms with r in it. I'm going to subtract the 7 pi over 4 r and move this 14 pi, add it to both sides, 14 pi. Now I'm going to factor out the r. This is 2 pi minus 7 pi over 4. Well, hold it. This is like 2 minus 7 fourths, right? 2 minus 7 fourths is, how many fourths is 2? That's 8 fourths. Minus 7 fourths, which is just 1 fourth. So this part is just pi over 4 times r equals 14 pi. I've run out of room, but let's do it up here. If we multiply both sides by 4 over pi times the pi over 4 r, and we take the 4 over pi times the 14 pi, then these cancel, of course, to give you just r on the left. And this is over 1, so this pi cancels that. 4 times 14 is 40 and 16. If you're doing that multiplication in your head, 4 times 10, 4 times 4, which is 56. They don't give us any units, so r equals 56. Well, there's 4 steps there. I changed the little bitty equation, s equals r theta, and used circumference. Had to subtract using pi. Oh my gosh. Okay, the next one. Number 8. Let's go to a new screen. Find the measure of each central angle in radians. I guess in a sense it's find the theta in radians. So we're given this picture. Let's see, getting better at these circles. 8 has this drawn in. Theta is right in here. R is 4. this length right here is 6. So, S equals r theta, just so theta is in radians. We want that theta in radians. S is 6. R is 4 times theta in radians. So 6/4 equals theta in radians. Well, I guess we can reduce it. Divide by 2, we get 3/2. So that's the number of radii, 1.5 radiuses. Next, number 18. Directions: find the length to 3 significant digits for each intercepted by a central angle theta in the circle of radius r. So 18, what do they give us? R is 12.4 feet. Theta is 330 degrees. And what are we supposed to find again? The length to 3 significant digits for each arc. So let's draw our picture. 330 degrees, let's start it here, goes all the way around until we get, so there's 30 degrees left, right? If this is 330 degrees, this must be 30 degrees. The radius is 12.4 feet. S equals r theta in radians. S, we don't know. That's this part right here. The radius, 12.4 feet. Don't forget the feet when you're all done. That's what our S will be, because radians are just the number. Now, 30 degrees, that should be one that you remember. That is pi over 6. So we get 12.4. Now I guess we can write this down here, times pi, all divided by 6. We need 3 significant digits, it says. 3 sig fig. So, if we pull up our calculator, I guess we'll put it over here. Turn it on. 12.4 times pi divided by 6. 3 sig figs is 6.49, right? Okay, so let me put this down. Tap this so I can what was that number again? You guys are supposed to remember that. 6.49. Okay. So we get 6.49, and it was feet. Okay. We can do one more problem on this little 15-minute video, number 24. Let's go to the next screen. Number 24. So 24. Find the distance in kilometers between the cities assuming they lie on the same north-south line. So let's do a little bit of a precursor. We don't have a lot of time here, but on the globe, all the longitudinal lines meet at the north and south pole. Right? But we're going to assume, because this is such a large thing, that these will be parallel when that's necessary. Latitudinal lines are always parallel. The neat thing about this, the latitudinal lines get smaller as you get to the poles, shorter circles, a bit smaller circles. The longitudinal lines are always the same circles. And any circle that has a center of the Earth as its center is called a great circle. So what they're saying is that these two cities are on a great circle whose center is the center of the Earth. For number 24, Halifax, Nova Scotia is 45 north, Buenos Aires is 34 south. So here's the equator at 0 degrees. Halifax is at 45 degrees north. Buenos Aires, Argentina, is 34 degrees south. This is north. This is south. Buenos Aires. Okay, and we need the distance between the two. Well, when you measure from the central, then these angles are the same, the 45 degrees and the 34 degrees. That central angle is the same in degrees as this intercepted arc. So that's sort of nice. But remember, we need radians when you start measuring distances, because we need this whole thing. So 45 degrees and 34 degrees is 79 degrees. We need that in radians. So 79 degrees times pi over 180 degrees. Nothing cancels very nice, I think. So that's the angle. Theta in radians. The degrees cancel. That's the only thing, but there's no nice number cancels. This is theta in radians. The radius of the Earth, we got to look that up. For kilometers, the radius of the Earth is 6,400 approximately kilometers. So, we can then find this, and I'm going to run out of time, so I got to do this sort of quickly. S equals r theta in radians. S, the distance between the cities, is r, the 6,400 kilometers, times this number up here. But we're going to run out of time here in just 2 seconds. So this is the third part of Trig 3.2. Applications of radian measure. I wanted to finish this one just to make sure that you didn't think that this is how you could turn in a problem. So this is what's kilometers. If we take the 6,400 times the 79 times the pi, divide by 180, what do we get? Well, once again, we're going to pull up our calculator. So let's clear this out. 6,400 times 79 times pi divided by 180. $8,824,385. So let me put that here. 8. What a memory. Let's see, what's that? 8,824,385. 8,824,385. 8, 8. 2, 4. 3, 8, 5. These are, because we're talking about kilometers. Now, the question is, how much of this can we use? We can't go with the 6400. That's one of those exact numbers. We're to the nearest degree, and so when we were looking at that table before and talking about what do you do when you get it to the nearest degree, well, we're supposed to do it to the nearest two significant figures. So with all these, we can get two significant figures just using the 8, 8 kilometers. I'm not sure what's the best thing here. I guess I'll try to guide you on a test question a little bit better than that. Okay, that's number 24. How about number 32? Number 32, they've got rotating wheels. You're supposed to repeat exercise 31, but let's draw the wheels first. We've got a smaller wheel and a larger wheel. The smaller wheel is 11.7 for its radius. This is in centimeters. The larger wheel, you just know is R. They say oh, I guess this has changed because this is no longer problem 31. So they're using smaller wheel 14.6 inches. It rotates at 120 degrees. The larger wheel rotates 60 degrees. Okay. So we're supposed to find the radius of the larger wheel. We're still supposed to find R. That's from 31. But now we've got this new radius for the smaller one. So how do we set this up? Well, it's for these types of problems, it's important to recognize both of these they're contacting each other. So when they rotate, the distance on the edge, part of the circumference, the S, is the same. So if we have S for the smaller, which is R, that's the 14.6, times the theta, well, 120 degrees. So over here, it's, if you change it into radians, which you need to, it is 2 pi over 3s, 260 degrees. So this is r theta, which is 2 pi over 3. That's what the distance s that this rotates along that circumference. The s for the larger circle is still r theta. We don't know r, though. 60 degrees is a pi over 3. These two are really the same because they're touching. That distance it travels for the small is the distance it's traveled for the large. Also, we can then put in the 14.6 times 2 pi over 3, and this is pi r over 3. Well, if these are both over 3, then we can multiply both sides by 3 and get rid of that. 2 times 14.6 is really, 2 times 6 is 12, carry the 1, 8, and then 9. So 2 times 4 is 8, plus 1 is 9, and then 2. So 29.2 pi is equal to pi r. Divide both sides by pi, and we get 29.2. In this problem, it was inches for the radius of that larger one. When these are touching, we know that the amount that this moves is the same as the amount that that moves. Okay. The next one, 36. Car speedometer. Speedometer for Terry's Honda CR-V is designed to be accurate with tires of radius 14. So let me just going to draw a tire of radius 14 inches. A. Find the number of rotations of a tire in 1 hour. Number of rot in 1 hour. If it's driven at 55. So if it's 55 miles per hour, and I need rot per hour. If that makes sense. So I've got the per hour, okay. I need to change these miles into a rotation. So I need to introduce rotations and get rid of miles. So how do what fractions can I use here? Well, instead of miles, I guess we may have to work through these in inches and stuff, because this is 14 inches is all I've got. I know that one rotation is a circumference is 2 pi times 14, or 28 pi inches. If I want to cancel the inches, I need to put inches up here and get to feet. I know that 12 inches is 1 foot. I also know that I don't want feet, I want miles. 5,280 feet, so I can cancel that feet, is 1 mile. So all those together will give me the miles cancel. I'm sorry, the miles eventually cancel. The rotations are left, and the hours are left. The inches cancel, and the feet cancel. So this final answer will be in rotations per hour. Let's see what that is. Move this over here. Clear this out. We got 55 times 1 times 12. Come on. 55 times 12 times the 5,280. We've got to divide that. Now we need parentheses because we're dividing by all this stuff. The 1, but that's okay, 28 pi. And that's all there is, the ones and the ones. So to make sure it divides by both 28 and pi. So what do we get here? 39615.938. And that's the number of rotations. So I'm going to write that here. 39,000 oops, 39,615.9938 rotations. Okay. Part B. Suppose that oversized tires, radius 16, are placed on the car. It looks really cool. If the car is now driven for 1 hour with a speedometer reading of 55, how far has the car gone? If the speed limit is 55, does Terry deserve a speeding ticket? Oh my gosh. So now we've got a tire, not 14, but 16-inch rims. And now, let's see, driven 1 hour, 55 miles per hour. How far? Okay. So, we know that once again, we know that the rotations do not change. Because you're going 55 miles an hour, the engine's turning that tire the same number of rotations. That's why we found this first. But the size of the tire means that our circumference has changed. 2 pi times now the 16, or 32 pi inches. So each rotation is now 32 pi inches. And this is just the number of rotations. So what are the rotations? 39,615.938 times the 32 pi. That gives us the inches at least. Let's bring up our calculator. We get that number we just had calculated times, notice it says answer, times 32 pi. Now this is the number of inches. I guess I don't really want to write that down. We're running out of time again. But we can change those inches by dividing by 12, because that will give us then the number of feet. And this is the number of feet we traveled, and if we divide that by 5,280 feet, that should give us the number of miles we've traveled, 62 miles, 0.857. In 1 hour, that's the miles per hour. Yes, he is speeding.